Physics is often presented as a collection of formulas. That's why it feels intimidating. But physics isn't really about equations. Equations are just a compressed language. Underneath them, physics is trying to answer a much simpler question. What stays the same when everything else changes? That question turns out to be more powerful than it sounds. The first place physics starts is motion. Things move, they fall, they slide, they collide. Sometimes they stop, sometimes they don't. Classical mechanics is the part of physics that describes this everyday behavior. If you throw a ball, it follows a predictable path. If you push a box across the floor, it slows down and stops. If you jump, you come back down. None of this feels mysterious because it matches our intuition. Classical mechanics works because at human scales and normal speeds, the universe behaves politely. To describe motion, physics introduces forces. A force is not a thing you can hold. It's a description of influence. Gravity explains why objects accelerate downward. Friction explains why motion fades away. A push explains why speed or direction changes. Instead of asking what happens, forces let physics ask why it happens. But forces alone aren't enough. To really understand motion, physics introduces energy. Energy is often defined as the ability to do work, but that's abstract. A better way to think of energy is as a kind of universal currency. Movement has energy, height has energy, heat has energy, even objects at rest can store energy. Energy can be transferred, transformed, or spread out, but it never simply vanishes. It behaves like money in a closed system. You can move it between accounts, but the total balance doesn't disappear. This idea leads to one of the deepest insights in physics: conservation. Certain quantities in the universe are conserved, energy is conserved, momentum is conserved, electric charge is conserved. These laws don't tell you what will happen. They tell you what cannot happen. They act like accounting rules the universe never breaks. Once you understand conservation, physics starts to feel less like memorization and more like logic. If something changes in one place, something else must compensate somewhere else. As systems grow larger and more complex, another problem appears. Energy doesn't just move, it spreads. This is where thermodynamics enters. Thermodynamics studies what happens when energy flows and disperses. Hot objects cool down, engines lose efficiency, batteries drain. Even living systems constantly leak energy and need to be refueled. A useful way to think about this is mixing. If you pour hot water into cold water, the result is warm water. You never see the reverse happen on its own. Energy naturally spreads out. This tendency is captured by a concept called entropy. Entropy is often described as disorder, but that's misleading. A better description is how evenly energy is distributed. Highly concentrated energy is useful, spread out energy is not, and the universe strongly prefers the spread out version. That's why heat flows from hot to cold. That's why systems wear down. That's why time seems to have a direction. Entropy explains why some processes are irreversible, not because they're forbidden, but because reversing them would require an extraordinarily precise rearrangement of energy. So far, everything we've talked about applies to solid objects, gases, liquids, things you can touch. But not all motion looks like objects moving from place to place. Sometimes what moves is a disturbance. This brings us to waves. A wave isn't a thing traveling through space. It's a pattern moving through something else. When you shake a rope, the rope doesn't move across the room. The motion does. Sound is a wave moving through air. Ocean waves move through water. And light, surprisingly, is also a wave, even though it doesn't need a medium. Waves help explain resonance, interference, and why some signals amplify while others cancel out. They're the bridge between motion and something more abstract. That abstraction becomes unavoidable when physics starts dealing with fields. A field describes how influence exists throughout space. Instead of objects directly pulling on each other, fields say, space itself carries information about forces. This idea becomes central in electromagnetism. Electricity and magnetism aren't separate phenomena. They're two expressions of the same underlying interaction. Electric charges create electric fields. Moving charges create magnetic fields. Changing magnetic fields create electric currents. Electromagnetism explains light, radio waves, electronics, and almost all modern technology. It also introduces something unexpected: a universal speed limit. Light always travels at the same speed, regardless of how fast the source or observer is moving. This fact quietly breaks the assumptions of classical physics, and fixing that problem changes everything. Sorry friends, I wanted to upload this video in one go, but my potato PC couldn't handle it. So I'm uploading it in parts. Show your love so I can make part 2 and the final part. Until then, this is Ace signing off.